Okay, what we're going to do here is we're going to sketch the graph of a function. Sorry, I ran out of room and I decided rather than squeeze that in, I'll just go to the next line. So sorry that this is in ink and I had to just scratch that out. We're going to sketch the graph of f of x equal negative 2x cubed plus 3x squared plus 12x plus 2. And my approach is going to be to gather some information, create the sign table, and then let the sign table guide me. That's really organizing the information I've learned how to collect. And so what I'm always going to do here is I'm going to start by finding any intercepts that I can. And finding y-intercept is something that I can always do, okay? So I'm going to find intercepts. And so specifically, I look at the y-intercept. And remember how we find y-intercepts is that's where the graph crosses the y-axis, so x has to be 0. So we say, we know that the x value is 0, so we think let x equal 0, and then we go about finding y. And when we do that, of course, when x is 0 and we put 0 into the function, then we get from above the point x is 0 and y is 2. And so we have an x-intercept there, okay? Now, excuse me, a y-intercept. I just plugged 0 into the function. Now, when we go about finding x-intercepts, that can be that can be much more difficult, and we can have several x-intercepts. We'll never have more than one y-intercept, though. And so remember, this is more difficult generally. Okay, we'll just keep that in mind. Y-intercept should be easy. So in the case that we're looking for x-intercepts, there are points where we're on the x-axis, and so that means the y value is 0, so we basically think, well, we'll let y be 0, and we'll go out and find the x that goes with it. Now, when we do that, that really means, remember, f of x is the y value, so that means we have 0 for the f of x, and then we have the negative 2x cubed plus 3x squared plus 12x plus 2 here on the right side. And that's why I said that this is generally more difficult. We've got to solve a complicated equation. Now, if this is an equation that is relatively easy for us to solve, then we will go ahead. But in this case, you can see that we have to use some very sophisticated techniques like we've learned in college algebra to be able to solve that equation. We've got to find factors and then factor a little at a time until we can solve it. And that's distracting us from our main point, and we want a sketch of this graph. We don't need these. So in this case, we won't find them. If we can find them without great difficulty, it's useful. But if it's going to be a lot of difficulty here, we're just going to move on. Okay, now the next big task is to find the critical numbers of both the first and second derivative. Okay, those are the important values across the number line. So find the critical numbers for both the first derivative and for the second derivative. And so in the case of the first derivative, we calculate, and we get what? Negative 6x squared plus 6x plus 12. And so when we're finding these first derivative critical numbers, we set that equal to 0. We want to know what causes it to be 0. I mean, it's defined everywhere, so that's not an issue. And so I'm noticing here we can factor out a negative 6 on this left side, and if we do, we'll have what, an x squared minus an x and minus a 2 equals 0. And then we could divide both sides by negative 6 so that we just had x squared minus x minus 2 equals 0. And then we would go about factoring this left side, and when we do, we would have an x minus 2 times an x plus 1. And so we would see that we got two x values, a positive 2 and a negative 1. Okay, now I'm looking for the second derivative critical number, so I need to find the second derivative. So I look over here at the first derivative and find out the second derivative is negative 12x plus 6. And so I need to know where that's equal to 0 and where that's undefined. It's undefined nowhere, so we just basically set that equal to 0, don't we? And we solve. In this case, we'll go through some steps, and I'm not going to spend all of our time right now. This is something that we should know how to do. I got an x value of 1/2. Now, let me kind of line this up. Let's because the next issue is this. We take these critical numbers and we put them from smallest to largest. So here's where -1 is, and I don't care about their positions being accurate. I want their positions to be relative to each other. So that the next biggest one will be a positive 1/2, won't it? And then the one after that will be a positive 2. So there are my 3 critical numbers written in order, and I'm thinking of them on the number line, because what I want to see is that this breaks the number line into 4 intervals. So we have the interval here from -infinity up to -1. And then between the 2 critical numbers, -1 and 1/2, we would have the interval from -1 to positive 1/2. And then we would have the interval from 1/2 to positive 2, and then finally 2 to infinity. So we see that this is how we're going to make out that left-hand column for the x values in our sign table. This will be at the top, and then we'll have this value of x next, and then this interval, and this value of x next, and then this interval, and this value of x next, and then this will be the interval, and of course that's going to be at the bottom of our table, in the very last row in the first column. So now we kind of have an idea of how to set the table up. So let's go to the next page, and let me draw out my table, and then we'll begin filling it in. Okay, I've gotten our table ready to go here. And so we want to start filling it in. And what we did on the previous page, remember, we had these intervals. And as we're thinking of the x-axis, the interval clear to the left was -infinity to -1. And then we found out that, of course, x equal -1, or in our work, we found out that that was a critical number. So we listed it separately. And then, of course, the next interval was from -1 to positive 1/2, okay, as we looked at that number line. So we're reading the number line, remember, from left to right, but we're going from top to bottom. And so then the next value that we come across is that critical number 1/2. There we have it. And then we have the interval from 1/2 to positive 2. And then we have the critical number that is 2, and then we have the interval from 2 to infinity. So now we have that left side of our sign table completed. Then we go back and we say, okay, let's put a zeros in for the first derivative for those critical numbers. So the first derivative had critical numbers at 2, so we have a 0 for that position. That's the first derivative. And it had a critical number at -1, and so we have a 0 in this position. Okay, and the second derivative had a critical number of 1/2, and so that was where the second derivative was a 0. That was when x is 1/2, and so we fill in a 0 in that position. Now, the next thing that needs to be done is we need to, for these values, the values where we actually have specific x's, we need to find the y value so that we can fill these places in. So for instance, in this position, we need to calculate f of -1. And I've calculated that to be -5. Now, I'm not going to waste your time by going through those calculations. All you're doing is putting -1 into the function and calculating the y value. Now, of course, the next value here, x equal 1/2, that's a little more tedious, isn't it? Because we have a fraction and we're putting it into the function f. But remember, that's all we're doing, is that we're putting 1/2 into the function f. So this value we get by putting 1/2 into the function f. And when we do, we get 17/2. Now, in terms of in 17/2, and I'm sorry that's so tiny, what we'll probably remember is that the easy way for us to think of that when we're plotting points, because that's what we're ultimately going to do, 17 over 2 is 8 1/2, isn't it? Okay. And then for the last value, x equal 2 here, we put the value into the function f, and we get the number 22. So we have y values of -5, of 8 1/2, and of 22, so we can already imagine that on our scaling system, we're going to have to scale our y-axis probably different than our x-axis. Okay. Now the next thing we're going to do is we're going to fill in the columns with pluses and minuses for f prime and f double prime. Now, what I would remind you of, I'm going to show this down below, but remember, for f prime, I've kind of put these pieces together here. For f prime, we had a critical number of -1 and of +2. So in terms of looking for a sign change, we really just need to consider, and normally I wouldn't write this down, I'm trying to explain. We would just need to consider the interval from -infinity to -1, which we see, okay? And so we need to test f prime in that interval. And so that means we just choose a value. We're used to this. We choose a value in the interval, like maybe a -2 or a -10, and we find out where the first derivative is positive or negative. And I've determined that it's negative, okay? Now, we might be led to believe when we look at what is that down here, well, when we look at this particular row, we might believe that we need to test that interval and then the interval from 1/2 to 2 as well, and also at x equal 1/2. But let me remind you, let's look down here, when we came up with the critical numbers for f prime, we got -1 and 2. And so we really just know that it's going to be between -1 and 2 that we're going to have a possibility of a change. And so once we know, and I really wouldn't mark in this usually this way, but all of these are going to have the same sign, either both all positive or all negative. And that issue is between the zeros of this first derivative, see the zeros that we have for the first derivative, the signs have to always be the same. So all we need to do is choose some value between -1 and 2. And we could check 0 in that case, right? We don't have to check all of those different intervals. And so when I went and checked, I found out that I checked for 0, and I found that I got a positive value for f prime. So that means I can fill in all of these with pluses. And then finally, we have the interval from 2 to infinity down here at the bottom, and that was part of the idea of the first derivative. And so that was an interval for we would have created for the first derivative. And so we test in that interval, and we find out the first derivative is negative. So now we're ready to move to the column f double prime. And notice in that column we have 1, 0. And so the idea, once again, is that's the critical number for the second derivative. And so all of the boxes above that 0 have to have the same sign, because we can't change unless we have a critical number. And all the boxes below that 0 have to have the same sign. So when I'm considering a test value, I can consider anything from -infinity up to 1/2. I can choose any x value, because all these boxes will have the same sign. And so in this case, I happen to choose an x equals 0. That falls in that interval. And I tested the second derivative, and I found out I got a plus, a plus, a plus. I got a plus, so all of those are pluses. And then on below 0 here, that is on the right side of 0, that's below in this column, I needed to test a value. So that's anywhere from 1/2 to infinity. So I could have tested a 1 or a 2, but I tested the second derivative appropriately, and I got a negative, and so I know I can fill all of those in with negatives. Now, I go row by row and create my conclusions. So in the first row, so in this row, I'm looking at a negative first derivative and a positive second derivative. Negative first derivative says decreasing. Positive first derivative says concave up. Now, in terms of the shape of the graph, we know that it has to look like that, don't we? Okay. Now, in the next row, we have a critical number of the first derivative. So what we're looking for is down that column, do we change signs? And yes, we go negative, 0, positive. So we change signs from negative to positive as we go across x equal -1. That means we have what? A relative maximum. We were decreasing and then we increased. So we know we have a relative maximum here. And the point is actually x is -1 and y is -5. We calculated that earlier. And again, we have a first derivative critical number and the second derivative is positive. Ooh. I'm sorry, I misinterpreted, didn't I? We have a relative, not maximum, a relative minimum. See, we were decreasing and then we increased. Oh, if we decrease and then increase, it's got to be a minimum. And the second derivative test would tell us if the second derivative is positive, we have a relative minimum. So I'm sorry for my mistake. Then I look at the next row, which is an interval. I see the first derivative has a positive. That means what? We're increasing. And the second derivative has a positive. And so that means we're concave up. So if we're increasing and concave up, we have that shape. And so if you put the first shape and the second shape together, yes, that looks like a minimum would occur in between those. And that's exactly what we have. Then we go to the next row, okay, where x is equal to 1/2. Well, that's a critical number of the second derivative. And so that's where we might have an inflection point of inflection. And we see in the second derivative column, we change from a plus to a minus as we move down that column past the 0. So that says, yes, we do have an inflection point, okay? So we know, hey, we have an inflection point. And we've already determined that point. It has an x value of 1/2 and a y value of 17/2. I'm just going to write 8 and 1/2. That will be easier for us to deal with. Okay, so it's going to change concavities. In the next the next row is the interval 1/2 to 2. We see we have a plus in the first derivative, a minus in the second. Plus in the first says we're increasing. And a minus in the second says we're concave down. Well, if we're increasing and concave down, then it looks like this, doesn't it? Okay, and so when we put those two pieces, of the one piece above and this piece, we see that it's at this position, isn't it, right there, that we have that change of concavity, and so that's where that inflection point is. Okay, next row, we have a value x equal 2, and that's a critical number of the first derivative. We can tell by looking at that 0. So we're looking to see whether we have a maximum or a minimum. And notice the sign changes as we move down the first derivative column. It goes from a plus, across 0, it goes to a negative. So we do have a relative maximum or minimum. Well, the plus says we're increasing and the minus says we're decreasing. So if we change from increasing to decreasing, we do have a relative maximum, don't we? Make sure I'm right this time. So it's a relative maximum. And the point is where x is 2 and y is 22. So the maximum is actually 22, but we're going to plot a point. Okay? And then we look at the very last row, and we see that, oh, the first derivative is negative, so that means we're decreasing. And the second derivative is positive, so we're concave down. Okay, and so if that happens, then it means that decreasing and concave down is this shape. And so we think of the two shapes, the one above and this one, and yes, that's how we see that we have a relative maximum. Now, I didn't show the specific calculations here, but it's important that, yes, that's going to take some scratch paper. You know, to find out these pluses and minuses takes a bit of work. But But once we know that those pluses and minuses, then it's easy for us to draw our conclusion. So the next thing we want to do is use this sign table as we did before to actually create the graph. So let me get my, let's get up a set of coordinate axes here so that we can make the graph. Okay, remember here I've got my axis set up, and notice, of course, I scaled differently on the x and y axis because my y values got as big as 22 here, didn't they? And so I know I needed to have, and I could have done a little differently. That's a 20, I see here. Okay. So let's plot points that we know that we have. For instance, we started out with a y-intercept of 0, 2. And so 0, 2 would be somewhere in here. Remember, I think we see 10 right here, and then there's a 5. So 2 would be roughly in here. And that's just a real rough guess there, okay? For what we're trying to accomplish, that's fine. And we happen to know in this case, oh, no, we don't know the x-intercepts, do we? I forgot. We didn't find them because it's too difficult to find. But what we do know is that we have a relative minimum at -1, -5. So that would be right here on top of this -1, wouldn't it? See, that would be right here. Okay? So we know we have a relative minimum there, so we have an idea of the shape of the graph right here, just kind of a rough idea. Okay, and then we also have a relative maximum at the point, 2, 22. So x is equal to 2 and y is 22, so that would be roughly here on the graph. And that is that's a relative maximum. So we know that the graph has basically this shape, doesn't it? Okay, now, oh, and we have an inflection point, 1/2, 8.5. That's a little bit hard for us to place because of the 8.5, but we know that 1/2 is here, and 8.5 would be, we'll say, roughly there. Now that's a point of inflection, so that's where we change concavity. And sometimes we can tell a lot, and sometimes just a slight change in concavity, so it's kind of hard to pick it up. Now, here's a little bit of a problem, is that for over here, for instance, on this relative maximum, I don't know how much it opens up. See, I'd kind of like to have an idea of where it crosses the x-axis, not the exact value, but does it cross between 2 and 3, or does it cross between 3 and 4, or does it cross between 4 and 5? And so what I did is I actually calculated, put an x value of 3 in for y, for a value of 3 in for x, and I calculated the y, and I got a 12. So I know the point 3, 12 is on my graph, and so that's roughly here. And then I did the same thing. I put a 4 in, and I got a -30 for y, and so that's way down here, isn't it? And so I know this graph is going to cross the x-axis between 3 and 4. Okay, and that's kind of helpful information. So what I know is over here on this part of the graph, it has to look like this, don't I? Whoops, I missed that point. But it has to look like that. Now, over here where this relative minimum is, again, I don't quite have an idea of how quickly that opens up. And so what I did over here is I put a -2 into the function f for x, and I got a 6 for my y value. So when x is -2, y is 6, so that's roughly right here, okay, somewhere in this neighborhood. And then I thought I wanted to have a pretty good graph, so I put a -3 in for x, and I calculated a y of 47. Woo! -3, y is 47, so that's way up here someplace, isn't it? See, that's clear up here in this neighborhood, somewhere up there. So now I have a good idea how this graph acts here. It does something like this, and remember we have a relative minimum right there. Okay, so now I kind of know both ends, and I know it goes through this point, and I'm still concave up, But when I get to this inflection point, it changes to concave down. And it's kind of hard for us to actually draw that change, but we see how those points connect now. And so we have a pretty darn good graph by just a few points and understanding the shape of the graph from our sine table.